Thanks very much, Joe. I'd like to reiterate that welcome and just introduce our first speaker, Professor Anna Marie Roos from the University of Lincoln. She's going to tell us about deconstructing the Copernican and Galilean controversy within the Catholic Church.
Good morning, everybody. Thank you for that nice introduction, and it's a real honor to be here today and be back in Oxford. So the premise of this talk is that the feud of Galileo, Copernicus, and the Catholic Church has been overblown, or at least fairly mischaracterized in popular treatments of history. In the latter case, we'll see some of the feud was brought by Galileo himself. Just a little note here that Copernicus's book that promoted a sun-centered universe, or a heliocentric universe from helios, for the Greek for sun, versus a traditional earth-centered universe, or geocentric, was only condemned by the Church 70 years after his death. The Copernican and Galilean controversies were thus not solely about the Church versus science. Based upon the instrumentation of the day, an earth-centered or a sun-centered system were equally plausible in the 17th century and able to explain observed astronomical movement. So first, I'm going to discuss the geocentric system of Aristotle and Ptolemy, and Copernicus's attempts to reform it. Finally, I'm going to explain why Galilean dynamics and astronomy was suggestive, but ultimately inadequate to prove a sun-centered universe and moving Earth at the time he was writing. And we'll talk a little bit about Galileo's hubris. He was a genius, he knew it, and you're going to see he had an ego the size of Florida. Since the 13th century, the Catholic Church had integrated a very uneasy synthesis of Aristotelian cosmology, which was the structure of the universe, and Ptolemaic astronomy. Cosmology really does concern, at this time, just the physical structure of the universe, and astronomy was part of what we call the quadrivium, or mathematical disciplines, and it plotted where and when the planets were. Essentially, astronomy was a calculating device. So let's go first to Aristotle's cosmological theory. It was first discussed in De Caelo on the heavens in 350 BC. This is a diagram for Peter Apian's Cosmographica in 1524. So you can see just from that, Aristotelian cosmology was prevalent for centuries and centuries and centuries, really until Copernicus. Now, he claims that the heavens have two distinct areas. The sublunar one, which is below the moon, you can see there, and the Earth is at the center here. And the Earth is surrounded by elements of water, air, and fire. The Earth, which was made of the very heaviest Earth element, rested immovably in its natural place at the center of the sublunar region. The watery sphere that surrounded that of Earth, but the boundaries between the two were a bit irregular because the higher parts of the land projected above the oceans which surrounded our globe. The sphere of the air was next to our atmosphere, and above it, but below the moon, was a sphere of fire, which was the lightest of the elements and the transition to the eternal realms of the planets. So they did really believe that there was a sphere of fire above the air. You might say, well, why didn't we see flames in the air? Well, that was because the element of fire was thought to be transparent. If any of you read Dante, you'll know that Dante and Beatrice, when they're traveling to the moon, they actually go through the sphere of fire, and Dante describes it very beautifully. The sublunar realm was a realm of change and corruption. Each of the elements were constantly displaced from their spheres by the motions and influences passed down from the prima mobile, which we see there at the top, outer sphere. That was Aristotle's term for the sphere of rotating stars in the sun. So the stars were really thought to be in a wheel that moved around us. And if you look at the night sky, they really do appear to be doing that. They were thought to be a little over 1,000 at the day because that's what we could only see with the naked eye, and the universe was bounded, was not infinite. The earthly region, in turn, was surrounded by the orbs of the moon, sun, and the 5 planets, because those are the only ones that were known, as well as the prima mobile and what was called the crystalline and empyrean heavens. The heavenly domain, beginning with the moon and extending upwards to the celestial heaven, was considered perfect and unchanging. It was composed not of earth, air, water, and fire, but a special 5th element called the ether, which was perfect and shining and noble. Aristotle was absolutely convinced that the celestial ether was incorruptible and it composed unchangeable heavens. He posited that the planetary orbits were solid crystalline spheres made of the ether, to which the perfectly polished planetary bodies, also made of the ether, were firmly attached. Now you might say to yourself, well, okay, so I'm looking up at the moon, yeah, and it doesn't look perfect to me. It looks like there's spots, there's macula all over it. Well, Aristotle said, he said that's because it was sort of in that halfway house between the imperfect and the perfect. And so it had areas of denser ether and rarer ether, and the denser ether was the spots. Now, I call that a bit of hand-waving, but it seemed to suffice at the time. The ether, like earth, air, water, and fire, determined the movement of the object it composed. And this is what's really interesting about Aristotelian physics. It's not based on mass, like we think of as quantitative. It was primarily qualitative. The composition of the element determined how it moved. Isn't that interesting? Aristotle believed that the composition of a body decided it's what he called its natural motion, the motion which it would undergo spontaneously without any external force. Everything moved had to have a mover. There's no concept of inertia in Aristotelian physics. Natural motion could be linear or it could be circular. In the case of earth, air, water, and fire, their natural motion was either up or it was down, from to or to center of the earth. Fire and air were thought to rise naturally. Air goes up to the atmosphere, its natural motion was upwards. Aristotle said a candle flame, the fire of the candle flame seems to want to go upwards to that sphere of fire that was up there, as candle flames pointed upwards. Water and earth, however, were thought to fall naturally due to observations of rain going to the oceans and rivers, and simply gravity. If I would drop this prompt here, which I wouldn't do, I would say it's made of the earth element. It would go down to its earth, right down here to its natural place. It would fall naturally downwards. Natural motion. Aristotle thought, however, there is in addition another type of body whose natural motion was circular, nobler, and eternal. He concluded bodies to which circular motion were natural were to be identified with the ether, of which the heavenly bodies were composed. So the heavenly bodies are made of ether, the natural motion is circular, that's why they move around us in circular orbits. Now, in the second book of On the Heavens, Aristotle also argues that the shape of the heavens must be spherical, as the circle was the primary shape in nature. Once he's established that the shape of the planetary orbits were circular, he had to provide an explanation for the motion itself. He conceptualized what we think of God as an unmoved mover that functioned as an object of love and desire for the soul that animated the body of the outmost sphere of the fixed stars, the prima mobile. The prima mobile rotated at an enormous speed every 24 hours and communicated its motion to the planetary orbital spheres. Later, Catholic thinkers like Aquinas called this unmoved mover God, and that's how they incorporated it within the Christian tradition. That's why it lasted so long. Although Aristotle's Earth-centered cosmology explained why the planets moved, it did not explain where the planets would be at any given time. Aristotle's universe of nested spheres and uniform circular motion orbits also did not provide an explanation for what we observe the planets to move as. The planets actually don't go above us in a purely circular motion. They actually appear to us to loop or do a retrograde motion. So this was a bit of a conundrum. So if you wanted to explain how the planets moved actually, or at least a mathematical model of how you thought they moved, you didn't look at Aristotle. That's cosmology. You turned to Ptolemy. You turned to astronomy, which told you where the planets were at every given time. And you looked at his Almagest, translated as his great book, which was written in 150 AD. This is a little animation of how Mars appears from the Earth to move. It moves in this loop. It seems to go ahead of us and then behind us, and that's called retrograde motion. The Greeks called it a hippopede, or a horse fetter. The term planets actually comes from the Greek planetes, or wanderers, and retrograde motion, however, is only an apparent change of the movement of a planet through the sky. It's not real, and that the planet does not start moving backwards in its orbit. It just appears to do so because of the relative positions of the planet and Earth and how they're moving around the sun. So let's see if this GIF works. There we go. No expenses were spared on this GIF. All right, so we can see here that the Earth is moving around the sun here, and the red is Mars. And as this repeats, what you're going to see, as it loops around again, at this point, the Earth looks like it's parallel to Mars. Then it appears from our viewpoint that Mars is behind us because this is a different orbit. And then Mars appears to be ahead of us. And if you want to plot it, if you don't believe me, you can actually do this on this diagram here, where the blue is Earth, The red is Mars. You can see they're parallel here. It's position 1. Mars appears to be ahead of us. Position 2. Mars appears to be parallel again. Position 3. Position 4 a little bit behind us, and then a bit more parallel. And so we can sort of track its motion across the sky. So how was Ptolemy going to explain this? It's explained really beautifully by a sun-centered system. But if you use an Earth-centered system, how is he going to do it? Well, he accepted the following order for celestial objects in the solar system. Earth at the center, Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn. But he realized, as had an earlier thinker called Hipparchus, that the inequalities in the motions of these heavenly bodies necessitated a mathematical system involving 2 constructions, deferents and epicycles. In this way, we could account for the movements in terms of uniform circular motion. So another gift, no expense spared. All right, so we have Earth at the center here, and the outer circle, the one in yellow, that is called the deferent, the big wheel, and we have Mars out here. And the little wheel is called an epicycle. Now you can see here in this mathematical construction that not only does Mars revolve on the big wheel, the yellow bit, the deferent, but it also at the same time loops around a smaller circle called the epicycle. If you're having trouble visualizing this, you can think of this as when you're on the London Eye, okay? If you're on the London Eye, and the center, where the Earth is sort of the pivot, and you're in a carriage on the wheel, if you just had the deferent motion, you just go around it in a circle, yeah? But let's say something malfunctioned with the London Eye, okay? And you're in the carriage, and instead of the carriage being steady, carrying you around this way, there's something wrong with the axle of the carriage, and it also rotates as you're going around, like this. All right? That would be quite a wild ride. But what happens as a result of that is that the planet appears to loop around, okay? So in Ptolemy's mathematical construction, right, he could vary the size of the deferent, he could vary the speeds of the rotation of the epicycle and the deferent, and he could add more epicycles. And he could, by a combination of circles, create curves that mimicked the actual path of planets across the sky. Now, as Ptolemy's naked eye observations of the stars were pretty accurate, the tables in his Almagest were very readily accessible, and his system of epicycles provides a model to predict planetary movement. His system really dominates the ancient world. And this is the model that both Copernicus, with his sun-centered system, and Galileo, who spent his career studying motion and positing the motion of the Earth, had to disprove. And that was a really tall order. So here's Copernicus. This is a portrait from the town hall in Turin. He was from the area we now know as Poland. Copernicus was, I guess I could best describe him, he wasn't just a graduate student, he was a gradual student. He was in school forever. He had a very wealthy Uncle Lucas who funded his study because Lucas wanted a personal physician around him and sort of a learned attendant. And so he sent Copernicus. Copernicus spent quite a lot of time in Italy. And Copernicus, in being Italy, this is the height of the Renaissance, he's looking at the works of the ancient Greek astronomers, and he got particularly interested in the work of Pythagoras, and this becomes important for a reason I'll explain later. So, in 1543, the year he died, Copernicus published this book called the De Revolutionibus, on the revolution of the heavenly spheres. And it's really been very much a traditional benchmark for the determination of medieval conceptions of the universe. The introduction of heliocentrism, or a sun-centered system, shatters this distinction between the corrupt earthly sublunar realm, with earth, water, and fire being mutable, and the perfections of the heavens and its ether, which had been established by Aristotle and popularized by Ptolemaic astronomy. There's a really good author by the name of Edward Grant who did a book called Planets, Stars, and Orbs. I highly recommend it if you're interested in this. He said, by making the Earth just another planet, Nicholas Copernicus hurls an implicit challenge to the concept of incorruptibility. As a planet, the heretofore imperfect Earth was as perfect as the other planets. Or conversely, the previously perfect planets were now as imperfect as the Earth. So why did Copernicus make the decision to support a sun-centered universe? Well, remember when I mentioned before, he got very interested and he was a student in Pythagoras. He revives what he thought were ideas of Pythagoras. In the 16th and 17th century, Pythagoras' teaching were seen as is actually a return to the ancient wisdom, the sapientia, the basis of truth. The Pythagoreans were a sect in 6th century BC of Greek mathematicians. They believed that all of the universe could be explained by mathematical laws. And when Copernicus studied Pythagoras, he thought the Pythagoreans said that the universe was sun-centered, that the sun was at the center of what we now know as the solar system. And that spurred him to do the De Revolutionibus. That was one of the reasons. Unfortunately for Copernicus, the Pythagoreans said no such thing. The Pythagoreans actually said that there was a central fire at the center of the universe, and the Earth and the sun moved around that central fire. So this is one of these historical mistakes that leads to a great breakthrough. And history of science is like that. It happens all the time. So he had a mistaken interpretation of Pythagoras that led him to adopt the heliocentric system. Another thing he realized is that a heliocentric system would solve the problem of retrograde motion without the need for epicycles. So here are two of our magnificent gifts here. And we have the system of Ptolemy's on the left, where we have to use an epicycle and a deferent. But Copernicus realized if we had a sun-centered system here on the right, when it comes up, we don't need those bloody epicycles anymore. And it seemed to him to be much simpler and much more beautiful. And in fact, aesthetics plays a huge role in the revolutions of the heavenly spheres. He actually writes a really impassioned encomium to the sun in his work. In the center of all, he says, rests the sun. For who would place this lamp of a very beautiful temple in another or better place than this where from it can illuminate everything at the same time? Beauty in science is important. It is. Scientists are very interested in simple, beautiful mathematical laws, so it does play a role. Now, we would think that such a very beautiful system would be accepted immediately, right? Well, in the first 7 decades following the publication of Copernicus' De Revolutionibus, there was almost no rejection of heliocentricity on religious grounds, not at all, because it was a hypothesis. He said this is possible how the universe could be. But there was very little acceptance by astronomers because of the substantial scientific problems the theory entailed, problems associated with the physics of a moving Earth. It was about the physics that was problematic. Now, what problems did 16th century and 17th century astronomers have with the Copernican theory? The first thing is Copernicus postulated that the orbits of the planets were purely circular, just as Ptolemy did, just as Aristotle did. However, in 1609, an astronomer named Johannes Kepler actually showed they're not. They're actually elongated ovals or ellipses. Copernicus himself did not do very many astronomical observations himself. He relied on Ptolemaic tables revised by a gentleman named Regiomontanus. People often said that if Regiomontanus wouldn't have fiddled, Copernicus wouldn't have danced. And so the Copernican tables offered a very only slight accuracy in predicting planetary positions over the Ptolemaic ones. So it's not really offering you a lot in terms of you just want to know where the planets are. He also offers very little physical explanation in the De Revolutionibus about how or why the Earth and the other planets moved, as the system was conceived before Newton's theory of gravity in the Principia in 1687. So when you look in the De Revolutionibus and you say, well, why do the planets move around? He says, well, they're spheres and they can't help but turn. That doesn't help you very much, yeah? Also think about it this way. If everything, gravity, things falling down, if something's falling down to its natural place, to an immovable Earth, and that explains why things falls down in Aristotle's system, what happens when you take that planet and you start it moving around? Why do things fall then? There's no explanation. Another thing that's very interesting is that if the Earth indeed moved, then astronomers should have been able to see something called parallax with regard to the fixed stars. So as the Earth moves around in our orbit, our point of view should be changing with regard to the fixed stars, producing an optical illusion of a change in their position. So stars should appear to move slightly side to side as the Earth revolves around the sun. One way you can do this is you can pretend that you're the Earth. You can put your thumb in front of your face. You can say, that's a star. You can pick any star you want to. It can be Betelgeuse. It can be the pole star, whatever flight fancy you have. And you can imagine, as you're in one part of the Earth, your Earth, and you're going around your orbit, From one part of your orbit, maybe perihelion, you're looking at the star from one point of view, and then from another point of your orbit, you're looking at it from another point of view. And if you experiment with this, and you just sort of wink and look at your thumb, what you'll see is this optical illusion of your thumb appears to move side to side. As it's close to you, that optical illusion is greater. As that's further from you, it's smaller. So a lot of astronomers said, well, okay, it's the Earth that's moving around Copernicans, why don't you see parallax? Well, parallax does exist. We do see an optical illusion, but what the astronomers in the 16th and 17th century did not realize is how far away the stars are from us. The parallax angle is very, very tiny, and you need a really powerful telescope to see it. We don't actually see parallax until 1838 with a powerful telescope. It's used to this day, however, to calculate stellar distance, just by a little trigonometry. And of course, we finally get to the biblical reason. You can see there's been lots of astronomical reasons. I mean, there's an important biblical reason. The Lord commanded the sun to stand still in Joshua 10:12. And if the sun wasn't moving, how could the Lord command it to stand still? So that's important. But it's only one reason of many that Copernicanism really was a mixed bag. Sense experience is also important. The Earth doesn't feel like it's moving. It moves very fast. It spins and rotates at a speed of 1,000 miles per hour, and it orbits the sun at a speed of about 67 miles per hour. I can put miles and kilometers because I'm American and we like imperial, so sorry about that. We don't feel any of this motion because the speeds are really constant, and the spinning and orbital speeds of Earth stay the same, so we don't feel the acceleration and deceleration. But they didn't know that. It seems to stand still. Okay, so it's a really mixed bag with Copernicanism. It solves retrograde motion beautifully. It's very aesthetic. However, it doesn't explain why the planets move. It doesn't explain the lack of parallax. It doesn't explain the biblical problems. It doesn't explain why we don't feel like we're moving. Hence, we have this gentleman come into the scene, Galileo. Now, Galileo dates are 1564 to 1642. This is the bust of him at his last home, the Jewel at Arcetri in Italy. He was an Italian astronomer, he was a physicist, he was an engineer. He sometimes described it as a polymath, and he was a great genius. In 1610, he published a very important work called the Sirius Nuncius, or the Starry Messenger. You can think of it as a papal nuncio, as a messenger if you want to inside reel the star. And he observed with a telescope. He did not invent a telescope, he designed a telescope based on an early invention by a Flemish man named Lippershey. He observed with a telescope, first with a 9-power one, then with a 15-power one, very simple, concave, convex lens in the tube, that Jupiter had its own moons. He saw that Venus appeared in phases, similar to those of Earth's moon, which suggested that Venus orbited the sun. And when he also pointed his telescope at the sky, he saw there were multitudes, more stars, revealed with the telescope, which contradicts this idea of a fixed sphere of stars bounding the universe. Here he is with his telescope, this apocryphal drawing, showing it off to the Venetians. Ooh, great, they can see the stars. The Venetians were really probably more interested in this telescope because, they're a maritime republic in this period. They also invented naval insurance. They wanted to use that telescope to see which ships coming over the horizon happened to make it safely into port and weren't pirated, so that the insurers could cash in on their bets, essentially. And Galileo got a very nice lifetime pension from the Venetians for that invention. This is an example from the Sirius Nuncius, a page from it, and there's a wonderful astronomer called Ernie Wright. You can see here, these are the moons of Jupiter. It's Jupiter with the little dots around it, the moons, and Ernie actually trained his telescope up there to see how accurate was Galileo in his observations of the moons of Jupiter. And he was damn accurate. And it's incredible considering he had about a 15-power telescope and probably not a great, that's difficult to do. Naked eye observations, this is really hard. And Ernie actually plotted, you can see Jupiter here with the moons of Io, Europa, Ganymede, and Callisto relative to Jupiter. And this thing is, you can see how Galileo's, the asteroids are the moons, and the circle here is Jupiter because he's dealing with typographic symbols in his book. And Ernie went ahead and reproduced these observations that Galileo did from 7 January to 2nd March, 1610. He did 64 observations of positions of these 4 moons, and they're absolutely spot on the money. So this is not to take away from Galileo's achievement. He also looked up at the moon, pointed his telescope up there, and he did not see a perfect shining sphere whatsoever as areas of rarer and greater density. He saw a jagged moon, nothing like that big of a crater on it. That was exaggerated by effect for Galileo to make a splash, but he sees rugosities and mountains and things on here. Later after the conference, there will be a set of PDFs on the website. I have a little sheet in there how Galileo calculated one mountain on the moon was 4 miles using a very clever combination of observation and trigonometry, and you can look at that. So this seemed to suggest that the Earth was nothing special, that the other planets were sort of like other Earths, and it seemed to, again, shatter this distinction between the sublunar area and the heavenly perfect area that Aristotle has suggested. That seemed to be a bit dodgy, right? Okay, this also shows you, this is Galileo's sketch of the stars in Orion's belt and sword, compared with a modern day photograph of the right. Galileo realized very quickly that we probably may not have a bounded sphere of stars that rotates around us, that perhaps of that bounded universe that Aristotle had postulated was infinite. All these things are extremely suggestive of a heliocentric system and a more infinite universe, but they don't prove it because Galileo did not have proof that the Earth moved. Not yet. And that's something he worked on for the rest of his life. We also have to consider this, that there was another rival planetary system that was around at the time of Ptolemy and Galileo, or Galileo and Copernicus. Tycho de Broglie, 1546 to 1601. He was a Danish nobleman. He's surrounded here by all the coats of arms as his ancestors. He was a very impetuous gentleman. Yes, he did have a gold nose. He got it cut off in a duel with another astronomer who he was fighting over rival theories. And Tycho had a really ingenious solution to these problems of the solar system. He postulated what we call a halfway house system. Now, he said that it's geocentric, the Earth is at the center. But rather than having all the other planets, including the Sun, go around the Earth, as in the Aristotelian or Ptolemaic system, what he did is he had the Sun go around the Earth, but all the other planets going around the Sun. So he sort of combines the two together. Now, what advantage did this give you? Well, first of all, for a lot of Jesuits and church authorities, Tycho's system does not contradict Scripture. The Earth is standing still. It preserves Aristotelian physics, because things still fall to the natural place to an immovable Earth. It explained retrograde motion without the need for epicycles. It explains the absence of observed parallax, because the Earth is stationary. And Tycho's data was extremely accurate. He was the best naked eye astronomer before the invention of the telescope. So a lot of church authorities accepted this one. They said, this is the one to go. Again, we're dealing with astronomy, mostly. Some religion, but astronomy. So these are important steps down the road to heliocentricity, but none of these discoveries were definitive proof of heliocentricity, but they've refuted significant aspects of the accepted Aristotelian cosmology and Ptolemaic geocentric astronomy. But Galileo does not want to compromise. He wants to establish heliocentricity. So, the trial of Galileo, and this is after, I've come to this conclusion after long talks with a lot of historians of science, and one wonderful guy named Tony Christie, who runs a wonderful blog called Renaissance Mathematicus. I'm always a little bit hesitant to recommend blogs, but this one is extraordinary. The trial of Galileo has been traditionally presented as this classic confrontation between the superstitions of religion and the innovations of science and truth. And it's true, absolutely. The Inquisition, they condemned Copernicanism as contrary to Holy Writ. They do bring Galileo to trial for the publication of a work called The Dialogue of the Two Chief World Systems in 1630, in which he supports heliocentrism. But to state that the Catholic Church was anti-scientific, and dogmatic, and Galileo was a defender of truth, is simplifying the historical events to an absolutely huge degree. First thing I want to say is the Catholic Jesuits were not superstitious. They were some of the best astronomers of their day in the 17th century. Christopher Scheiner's a shining example. He discovered sunspots, although Galileo tried to take the credit away from him. And Galileo, for a lot of his career, enjoyed tremendous patronage from the papacy and esteem. But I will say, Galileo had a very abrasive personality. He made enemies very easily, and his actions before the trial may have led to the dispute occurring in the first place. So he has very influential friends within the church. They include Cardinal Maffeo Barberini, who becomes a future Pope Urban VIII. They're very much aware of the situation I've described, where there's an open debate of the validity of Copernicanism. And they warn Galileo to proceed with caution. They tell him, if you treat Copernicanism as a hypothesis and you want to discuss it as an astronomical model, that's cool. But if you want to discuss it as physical truth, buddy, you better have the physical proof that the Earth moves. And that was the condition. Galileo, I think, ignored this very sensible advice, and the matter came to a head with something called a letter to Castelli, which was later published as a letter to the Grand Duchess of Christina, which is one of Galileo's patrons. So this is a letter here that's published in Florence, Tuscany. So there's a story with this. So late in 1613, there was a newly appointed professor of mathematics at the University of Pisa who called Benedetto Castelli, and he was a pupil of Galileo's, and he attended a lunch hosted by the Grand Duchess Christina, who had been one of Galileo's patrons. And Christina sort of expresses some doubts about Galileo's observations of the moons of Jupiter, and she considers the Copernican astronomy possibly heretical. So after the meal, she summons Castelli to her chamber, and then in the presence of other guests challenges him about these ideas of the mobility of the Earth. Galileo heard about this, got rather incensed, and he writes this very long letter to Castelli, supplying him with arguments to use against those quoting biblical passages against heliocentricity. Now, it's very interesting. The original holograph of this letter is in Britain. You would think it would be in Italy. We thought it was in Italy for a long time. It's in the Royal Society Library. We don't know how it got there. This is an open research question, actually. The mistake came about because the letter was misstated in an old catalog. And a young postdoc named Salvatore Ricciardo, very bright young man, saw this and realized, this is misstated. My God, this is the original letter. So any of you out there who want a PhD thesis, there you go. You can go look at this. You can go see it if you want to. Go talk to Keith Moore. He'd be very happy to show it to you. All right. So in this letter to the formal pupil of Castelli, a Benedictine monk and professor of mathematics at Pisa, Galileo sets forth his ideas on the relationship between science and religion. And it's a very short treatise in epistolary form. It's done as a letter because this is a period of the Republic of Letters. People didn't just write letters like private emails. They published sort of these very rhetorical letters to each other to argue a particular point of view. And the first scientific papers that were published in things like the Philosophical Transactions of the Royal Society were actually letters, so this is quite normal. The letter to this circulated very privately and widely, and it was designed to offer a response to objections from Aristotelian philosophers and theologians who regarded Copernican astronomy as a serious threat. And the opponents were very convinced of the incompatibility of the new astronomy with some passages in the Bible. Now, in order to support Copernicus's view and the freedom of scientific research, Galileo maintains a very clear-cut distinction between the realm of faith and that of scientific knowledge. And this is Salvatore Ricciardo's here, his words. He argues that the statements of the Bible about natural phenomena did not constitute valid reasons for drawing corresponding scientific conclusions. Galileo's argument, which was later set up much more systematically in the letter to the Grand Duchess Christina, Ricciardo says, marks a crucial step in the rise of modern culture since it claims the autonomy of science from the control of theological authority. And we see that, we go, hey, Galileo's a big hero for saying this. But that's not the way the church saw it whatsoever. You look at a theologian like Paul V, He said, if we're going to accept heliocentricity, then we have to abandon a literal interpretation of this and other passages in the Bible. And we are only prepared to make that concession if there's solid empirical evidence that the sun is at the center. Now, why was this sensitive? Think about the time with Galileo's writing, 17th century. What has happened to the Catholic Church in the past 2 centuries? The Protestant Reformation. The Protestant Reformation is a direct challenge to the Catholic Church's authority and its ability to interpret theology. And the Catholic Church is doing the Counter-Reformation. It's going against what Martin Luther had to say. So of course, it's more sensitive at this time to critiques. So the letter, when it comes out, triggers a 1616 suspension of Copernicus's De Revolutionibus, and it leads to Galileo being warned by Cardinal Bellarmine, one of the leading figures of the Inquisition, and then really outstanding Jesuit theologian, to abandon Copernican astronomy. And the Pope tells Bellarmine to inform Galileo of the Commission's judgment and forbid him from holding or teaching the heliocentric theory. The theory, heliocentricity is a statement of fact, was forbidden, but not the hypothesis. You could talk about his hypothesis any way you wanted. And that was a very important distinction. And here's the prohibition of Copernicanism on the 5th of March, 1616. I always remember that 5th of March is my birthday, so hooray for me. And it says that the Copernicus' work has to be suspended until corrections. That meant there were a few sentences in it that they found that were problematic, but they didn't condemn the whole book. Okay. So now we'll get to the trial of 1633. So Galileo's admonition stops the Copernican movement dead in its tracks, and he busies himself with other things. He tried to find a way to solve the problem of longitude, for instance. But in 1623, he received some very hopeful news. This guy, Maffeo Barberini, had been elected Pope as Pope Urban VIII. He had a fairly positive view of the arts and sciences. He was considered quite enlightened. And writing from Rome, the Pope's private secretary urged Galileo to resume publication of his ideas. And in the early part of his reign, the Pope has very long audiences with Galileo. They discuss things in the papal gardens. They talk about astronomy, they chat about physics, they chat about Galileo's telescopic redesigns. And Galileo was very encouraged by a Pope who seemed open to renewed debate and the merits of the Copernican system, so long as the arguments fell short of purporting to be a definite refutation of the Earth-centered universe. And Galileo is encouraged to begin work on a book that eventually will prove his undoing, the dialogue concerning the 2 chief world systems. Now, on 24th December 1629, he tells friends in Rome he's completed work on this dialogue on the 2 chief world systems. It's been described as the story of the mind of Galileo. It marshals all his arguments together for a sun-centered universe. It was a book for the educated public, not for specialists. It was written in a dialogue form. Why? It was an imitation of the Socratic dialogues way back when in the ancients, and to allow for free debate and discussion. Only 2 systems appear in the dialogues, the Ptolemaic and the Copernican. Tycho's system mysteriously is not there. Why? It offered a really good alternative and a really powerful argument about Galileo's promulgation of heliocentrism. He just leaves it out. Galileo inserted statements about the hypothetical character of the work in the preface and the conclusion, but it's not even-handed. And I would say it's very contrary to the instructions he was given by the Church to only discuss heliocentrism as a hypothesis. There's 3 Italian gentlemen in the book. Galileo uses a variety of arguments to lead his readers to accept Copernican theory. There's a character, Salviati, who is Galileo himself, a person described as supreme intellect. There is Sagredo, who is a Venetian nobleman, actually modeled after a friend of Galileo's, who's open-minded and hesitant to draw conclusions, who's a good listener. And then there's Simplicio. He's a straw man. He's a stubborn, literal-minded defender of the Earth-centered universe. Okay, and here's the frontispiece. These are not the 3 Italian gentlemen, confusingly enough. They're actually Aristotle and Ptolemy and Copernicus. Aristotle's on the left, Ptolemy is holding an Earth-centered armillary sphere, and Copernicus has a sun-centered model of the universe, and they're having this discussion. Okay? All right. Now, early news from Rome gives Galileo reason for optimism that his book will soon be published. It has to go through a chief licensor, Niccolo Riccardi. Riccardi says we can, take care of any theological problems with it. And when Galileo arrives in Rome in May 1630, he writes, "His Holiness has begun to treat of my affairs in a spirit which allows me to hope for a favorable result." Urban VIII reiterates to him, though, if the book treats the contending views hypothetically, not absolutely, we can publish it. And Galileo says, oh yes, of course. All right. Well, Galileo was, I think, a bit confident that he was going to win the day because he had what he called his secret weapon. He thought he had a theory of the tides that absolutely proved that the Earth moved, right? He was very inspired by the behavior of water when boats come to a halt. And he thought that the ebb and the flow of tides resulted similarly from the acceleration and deceleration of the oceans, sort of sloshing around. How did he say this? Well, he said that the tides were propelled by the dual motion of the Earth around the sun and around its own axis. And he said that because the direction of rotation of the Earth's annual and daily movements are the same, the speeds accumulate on the side of the Earth turned away from the sun. And he said the opposite happens on the side facing the sun. And between these points, the seawater is accelerated or deaccelerated, just like the water in the barge. The problem was with Galileo's theory, is other than it's wrong, is the tide, in his theory, the tides only occur once a day instead of twice. But he thinks that this is the secret to proving the Earth's motion and thus a heliocentric system. But he still really doesn't have definitive proof of a moving Earth. We know it's because of gravity, right? And this is from the National Observatory of Atmosphere in the United States. And we know it's really high tides and low tides. As the moon's position changes, two tidal bulges rotate around the Earth. The bulges represent high tides, while the corresponding flat sides indicate low tides. But again, Galileo's pre-gravity, pre-Newton. So it was realized soon after the book was published in February 1632. It sold out very quickly. It became the talk of the literary public, but it was realized very quickly it was a very thinly veiled brief for the Copernican model. And orders come down from Rome to suspend publication of the book. On 5th September, Pope Urban told Francesco Niccolini, "Your Galileo has ventured to meddle in things that he ought not, and with the most grave and dangerous subjects that can be stirred up these days. Jesuit enemies have Galileo, because he didn't make friends easily, convinced the Pope that the dialogue was just a thinly veiled brief of the Copernican system, and they also convinced him that the Pope's own arguments for physics, and particularly concerning the tides, were put into the mouth of the simple-minded Simplicio. And the Pope thought that Galileo was ridiculing him." Okay. So what happens? The trial. The boom is lowered. Now, we think of the Inquisition as people being thrown in the dungeon and chained and being tortured, and that did happen. They didn't treat Galileo like that. He was getting elderly. They showed him the instruments of torture, but they never tortured him. They wanted to frighten him. The Inquisition was actually very much of a judicial court. It was very procedural, right? So the Inquisitor of Florence showed up at Galileo's house and said, "Here's your summons. Present yourself to the Holy Office in Rome within a month." He goes to Rome. You can see there's a bit of a delay. He takes a little longer than a month. He has lots of excuses, but he eventually gets there. He surrendered to the Holy Office, and he faced Father Firenzuola, the Commissionary General of the Inquisition. And the counselors of the Inquisition look at the dialogue in the two chief rule system, and they prepare a 7-page evaluation. They conclude that Galileo in the book taught, defended, and showed that he held Copernican theory, and that while he claimed to discuss world models hypothetically, he gave the Copernican model a physical reality. He was sentenced on 22nd June 1633. He was released to the custody of the Florentine ambassador. Niccolini described Galileo, of course, as being extremely downcast over his punishment. Of course he was. He was transferred to Siena, and then he finally was placed under house arrest, and he moved into a small farmhouse in Arcetri. He grew blind there, and he died 9 years later in 1642. He didn't spend his imprisonment in a dungeon. He spent it in a rather pleasant villa called the Jewel, but it was still house imprisonment, so I'm not making light of that. He was near his daughter, who ironically was a nun, a illegitimate daughter, and she'd visit him. So I hope that this talk shows you that it wasn't a fait accompli that the Copernican system would be readily accepted. And the interpretation at Galileo's trial was a matter of an ignorant church in conflict with the heroic science was simplistic. With the publications of his Principia in 1687 and the theory of universal gravitation, it was finally explained how the planets moved around the sun, the correct interpretation of the tides, and the acceptance of the heliocentric system. Thank you very much.
Thank you very much, Professor Roos. We now have a few minutes for questions. Would you like to take questions from?
Oh, sure. I can take questions. Sorry,
Okay.
I didn't know
All
what
right.
to do here. Yep, I'm happy to take questions. Please go ahead. Yes.
Is it a myth that at his trial he did retract his views on heliocentricity?
Oh, yes. If you retracted your views and recanted your views, it was actually could be punishable by death if you did that. That's what happened to your daughter Bruno. So it's a complete myth. He would have been very stupid to do that. Yeah, absolutely.
What's the evidence that he knew about Tycho's model?
Oh, he knew about Tycho's model, absolutely. And I'll tell you why. He had an active correspondence with Johannes Kepler. And Kepler, of course, for a while worked for Tycho Brahe. So he knew about Tycho's model. Sure he did. He just didn't cover it because it contradicted his own desire to promote heliocentrism. But in fact, if you want to read some beautiful correspondence, do look at the stuff between Galileo and Kepler. There's this wonderful meeting of minds between the two as they discuss astronomy. And I mean, as we know, Kepler did the planetary laws and elliptical orbits and equal area sweep out equal times. And Kepler actually had it wasn't gravity, it was still, he imagined the sun is putting out almost like an invisible broomstick of force and pushing the planets around it, yeah. But I mean, it's beautiful correspondence. But oh yeah, Galileo knew about Tycho very well. Sure he did.
So, did this letter and the statement that maybe you should first look at the book of nature before you consult scripture on such matters, did that play any role at all in the trial?
Galileo.
What we see now as the basic conflict here.
Yeah. Galileo held that very privately. And in fact, when he was put in the custody of Archbishop Piccolomini, who was actually quite sympathetic to Galileo, they discussed such things. But it didn't play a formal.
I didn't have that at all.
Huh?
In the trial itself, there's nothing in the acts of the trial.
No, because the trial was very circumscribed. It was about purely did Galileo ignore the prohibition given him by Cardinal Bellarmine. Even that, there's some interesting historiography about that as well. Let me see if I can find it here. There's some debate over whether Galileo was told he couldn't hold, defend, and teach heliocentric hypothesis. Some people said that he was allowed to defend and teach it, but he couldn't hold it. So there's a bit of a problem with some of the evidence that the Inquisition presented. This is a big historiographic debate. You can look at Stillman Drake, and he talks a lot about that. He's a good author to discuss that problem. Yeah.
You mentioned that Galileo's book sold out. Do we know how many copies were printed and how many have survived? And also, why would the penalty for recanting your views be worse? Why would you only get death if you recanted?
Because once you swore that you would do penance in front of the Inquisition, if you recanted on your word and then went back to the other way, then it was seen as a direct contradiction to what they had given you. I mean, if you go down to the Martyrs' Memorial in Oxford, Yeah, and you look at the Protestant martyrs that are there, some of them were killed because they had said that they would actually go back to Catholicism, and then they actually recanted their views later, and they were actually killed for that. Some of them recanted under threat of torture, of course. But if you recanted, then you were said not to be following what the church told you to do. So that was very serious. I don't know the precise amount of copies that were done of the Dialogue of the Two Chief World Systems. I know there are a lot of them that survive. There's one really good copy, and you can see it online. It's at the University of Oklahoma, if you can believe that. They have a wonderful library called the Bezel, and that one actually has annotations in it in Galileo's hand, as he's sort of thinking about some of the things that he wrote about it. So if you want to look at that, that's a really good one.
So next question is from the gentleman in the third row here. And I'm going to take one more after that.
You mentioned that this was a period when the Protestant Church had been formed. What was its position with regard to the...
Oh, the Protestants actually were very much geocentrists because, I mean, Luther certainly was, because the Protestants had a very literal interpretation of the Bible. But I think as time went on and the evidence started mounting up, then we start seeing a softening of this position that perhaps the Bible was speaking in parables. It was a long period of time from when Luther rebelled against the church in the early 16th century to the 17th century. By the 17th century, I think among educated Catholic intellectuals, they had no trouble discussing Copernicanism as a hypothesis whatsoever. And I think some of them secretly thought that it probably was true, but they were waiting for the definitive proof. Because, I mean, think about it. It's a big thing to overturn, isn't it? You have to really know before you're going to say that these biblical passages were just stories designed to educate the public rather than literally true. Yeah.
Thanks. So the last question is from a gentleman at the back left. So microphone guy has a bit of ground to cover, I was going to say.
Hi, thank you very much for the excellent talk. I was just, from this, I'm thinking, is one way that we can conceptualize this so-called conflict or episode in history as kind of institutional dogmatism versus young heresy, in the sense that it's not kind of science versus religion, but actually institutions that have political, economic, and social interests, and will protect them. Because if so, then we can apply that potentially to scientific institutions as well.
I think that we need to, it's a really good question and a good point. I think that we need to, all history of science, in my opinion anyway, needs to be set in social, cultural, institutional context. And there's a really good book by Mario Biagioli called Galileo Courtier, which I recommend if you're interested in this aspect of it. It really shows how Galileo was playing a game of patronage. I mean, there's no National Science Foundation or, European Union or whatever funding for natural philosophy, as they called it at the time. He wanted support and he wanted patronage. And it shows how, Biagioli really shows how Galileo was playing a game of patronage, and he didn't play it for himself very well at the end. Yeah, and so, yeah, you need to put this stuff in socio and institutional context, but I don't buy that the church was dogmatic. I buy that it was in a position where it was defending its authority, but if it was going to overturn a key precept of its authority, that was in fact being brought to the fore of intellectual thought by Galileo himself, by his actions, that there needed to be a really good reason to do it. I don't know if that helps.
Okay, great. Thank you very much. I think we ought to thank Professor Roos again for a wonderful talk.